work that I talk about is joint work with Benson Farb. And it fits into this program of Gromof to classify finitely generated groups according to their asymptotic geometric properties. Now, what that means, Sergio mentioned it a little bit in the last talk, is that you want to classify finitely generated groups up to this relation of quasi-isometry. So, if you have two metric spaces, then a quasi-isometry between them is a map with two properties. So for some constants, first of all, it distorts distance by no more than this multiplicative amount with a little additive error. And second of all, this property alone is what Sergio referred to when he was talking about quasi-isometric embeddings. And you need a further property in order to make this relation invertible. And that is that every point in the range is within some bounded distance of the image. Okay, so this generates an equivalence relation on metric spaces, and so there was a principle, this rigidity principle, discovered a while ago by Milner and also by Schwarz, and I think it may have been discovered even more times. And it says that a finitely generated group, G, is with its word metric is quasi-isometric to any metric space on which it acts appropriately. So to any proper geodesic metric space X on which G acts properly discontinuously, co-compactly by isometry. So, for instance, universal cover of a compact manifold with fundamental group G, or the Cayley graph of G. So what this principle tells us is that, together with the fact that quasi-isometry is an equivalence relation, it tells us that a finitely generated group has a well-defined notion of geometry associated to it, namely a quasi-isometry class. And it tells us, in addition to that, that in order to study the geometry, the quasi-isometric geometry of a group, you're free to pick whatever space this group acts on. And oftentimes, the cleverer your choice of space, the more you'll learn about the group G, simply because the appropriate geometric properties are clearer in this choice of a space than in another choice. So, for example, if you're the fundamental group of a surface of genus 2, you should really choose the action on the hyperbolic plane rather than the action on the Cayley graph, because the appropriate geometry for that group is the geometry of the hyperbolic plane. The features of that geometry are much clearer. So the problem then, which was posed by Gromof, this is really a meta problem, is to classify finitely generated groups up to quasi-isometry. And let me give you a few examples of such classification theorems. You know, there's not really much hope of solving this problem completely. So really what you want to do is identify quasi-isometrically rigid classes of groups, find the different quasi-isometry classes within that one rigid class. So for example, Gromof's polynomial growth theorem says that a finitely generated group of polynomial growth is virtually nilpotent. And if you combine that with the fact that polynomial growth is a quasi-isometry invariant, and with Wolff's proof that nilpotent groups have polynomial growth, then you get that the class of nilpotent groups is quasi-isometrically rigid. And what I mean by that is that if G is a finitely generated group and G is quasi-isometric to a nilpotent group, then G is virtually nilpotent. It has a nilpotent subgroup of finite index. So there's a quasi-isometrically rigid class, the virtually nilpotent groups. Now, the classification of those groups into distinct quasi-isometry classes remains unknown to this day. The best result so far is a theorem of Pan-Su, which says that if you have two nilpotent groups, and if they are quasi-isometric, then, well, he produces a certain quasi-isometry invariant, and I'll just write the words down without at all saying what they mean. The graded Malchev-Lie algebras of G and H are isomorphic. And it remains unknown whether this quasi-isometry invariant is a complete invariant for nilpotent groups. So let me give you another example of a quasi-isometric rigidity theorem where the answer is complete, and that is...
Maybe not erase that.
Oh. Dookie. This isn't worth it. I'll just erase. So there's a theorem of Gromof and Sullivan which tells you what are the groups that are quasi-isometric to hyperbolic 3 space. Well, we know some of them, namely fundamental groups of closed hyperbolic 3 manifolds. There's more than that, namely fundamental groups of closed hyperbolic 3 orbifolds. And there's a few more. You can take a Cartesian product with a finite group. You can take some type of finite extension. The amazing thing is that that's all of them. So if G is a finitely generated group, and G is quasi-isometric to H3, then there exists a finite normal subgroup of G such that G mod n is isomorphic to the fundamental group of a closed hyperbolic 3 orbifold. Okay. And now this theorem has been extended to all lattices in semi-simple Lie groups. In the sense that it's known what the complete classification of these lattices are up to quasi-isometry, and quasi-isometric rigidity of all these lattices is known. You have similar theorems to the Gromof Sullivan theorem here. This is a vast result covering many, many, many different works by many, many, many different people. Okay. So where Benson and I got into this was in saying, okay, there's an obvious question that arises over here, which is there some way to extend this to solvable groups, maybe perhaps to some subclasses of solvable groups, such as polycyclic groups? So in the book by Gies and de la Harpe, they asked the question, are polycyclic groups quasi-isometrically rigid, are solvable groups quasi-isometrically rigid? And then the same question comes up over here, because there are, beyond the semi-simple land, there's now interesting solvable Lie groups, which you want to know quasi-isometric rigidity of. So the theorem that that we were able to prove is for, in some sense, the simplest class of virtually nilpotent finitely generated solvable groups, which are the solvable Baumschlag-Solitar groups, BS1n. They have a simple presentation, AB, where BAB inverse is a to the n, and take n greater than or equal to 2. And the first result that we had there is the classification of these groups among themselves up to quasi-isometry. So BS1n is quasi-isometric to BS1m if and only if the primitive root of these two integers is equal. So there exists an integer p and then integers r and s, so that n to p to the r equals n, p to the s equals m. So there's one quasi-isometry class for every power-free, for every integer which is not, every positive integer which is not a power. And then
P is prime?
No, it's an integer, natural number. And then the second result is a quasi-isometric rigidity theorem. So given a finitely generated group, if G is quasi-isometric to BS1m, then there exists a finite normal subgroup n, so that G mod n is, well, the correct words are abstractly commensurable to BS1m. We can actually say something stronger. Just as the cleanest way to state the Gromof Sullivan theorem is to look at hyperbolic 3 orbifolds, there's actually a slightly larger class of groups here where you allow yourself negative integers, where you replace A by a dihedral group, and in that larger class you get that the quotient lands right in there. Okay, so what I'd like to talk about today is about some parallels between the proof of this theorem and the proof of this theorem, and that's where the laminations come into the picture. And hopefully I'll have a chance to say just a little bit about some extensions of this theorem that we're working on. So one of the general methods of studying quasi-isometric rigidity is you ask yourself a question like this. If X is a metric space and G is a finitely generated group quasi-isometric to X, you want to know, well, does G act on X properly, discontinuously, co-compactly by isometries? Well, the answer might be no. So you don't really have too much of a hope for getting something. You don't really have any general hope of getting something that strong. But what you do have is that although you can't get an action on the nose, you get sort of the correct analog of an action in the world of quasi-isometries. So for each G, there is a KC quasi-isometry, which I'll write rho of G. Okay, so there's going to be some constants here. So instead of getting an isometry, you get a quasi-isometry. This is not an action because it doesn't respect composition, but it coarsely respects composition. So the distance from rho GH of X to rho G of rho H of X is bounded, and this is uniform of the G and the H and the X. And then there's also an analog of properly discontinuous and an analog of co-compact. I'm not going to write them down, but and so you get what I'll just call a quasi-action of G on X. And so now what you want to know is, okay, what groups can quasi-act on this space X? And hopefully you've chosen a good model space for your geometry. And so what happens over here in the Gromof Sullivan picture is that hyperbolic 3 space is so nice and so symmetric that the only groups which can quasi-act on it are groups which actually do act on it. So let me say then a few words about how to understand that in this setting. So here we have hyperbolic 3 space. Now, I'm going to change the model ever so slightly, and instead of thinking about the groups acting on hyperbolic 3 space, I'm going to think about groups acting on the unit tangent bundle of hyperbolic 3 space. This has a few nice foliations on it. First of all, there's the geodesic flow. So this is a foliation by lines. And then there's the weak unstable foliation of this flow. And one leaf of this weak unstable foliation consists of, you choose a point. I'll draw it one dimension down. This is the picture that Sergio just drew. You choose a point on the boundary and you look at all flow lines which end at that point. And then there's also the weak stable foliation where you look at here all leaves which start at a certain point on the boundary. Okay? So these two foliations here, the leaf space of the weak unstable foliation, well, there's one leaf for every point on the boundary. And it's an amazing coincidence, but the leaf space of the weak stable foliation also happens to be the boundary. Okay. Oh, I'm sorry. I'm sorry. You're absolutely right. This should be stable and unstable. Thank you. Thank you. Okay. So what I'd like to do now is to describe how a lot of this structure lives over in the land of solvable groups, except for this coincidence here. This coincidence between the stable and unstable leaf spaces breaks down. But enough of this structure lives to enable you to, well, I haven't said what happens now when you have a quasi-isometry. So let me say that now in this context before I go on to the solvable groups. So now suppose you have a group quasi-isometric to hyperbolic 3 space. So you now have this quasi-action. Rho of G for each element in the group. And now you want to know, what does this quasi-action do to the geodesic flow, for example? That's the main thing you want to do. Now there's the Morse lemma, which says that every quasi-geodesic in hyperbolic 3 space stays a bounded distance. Every bi-infinite quasi-geodesic in hyperbolic 3 space stays a bounded distance from a unique geodesic. Okay. Maybe he had a lot of lemmas. I guess I'm sort of using maybe terminology that's used among a somewhat ingrown group here. Every bi-infinite quasi-geodesic stays a bounded distance from a unique geodesic. And what this implies is that the group G coarsely preserves, coarsely respects the foliation by geodesic flow lines. Okay? And then that has as a consequence that G actually acts, not just quasi-acts, but it actually acts on the leaf spaces of the stable and unstable foliation. And then coincidence of coincidences, these are the same action. So G acts on the 2-sphere. Okay? Now, the remainder of the game is to now find out what the analytic quality of this action is. And what you do is you discover that the action of G on S2 is uniformly quasi-conformal. And then there's a theorem of Sullivan which says that every uniformly quasi-conformal group action on the 2-sphere is quasi-conformally conjugate to a conformal action. So G acts conformally on the 2-sphere. What I should really say is the original action is, you know, quasi-conformally conjugated to a conformal action. And that's enough now to get the conclusion of the Gromof Sullivan rigidity theorem. Okay. So I would like to show you now how these types of structures and these types of arguments can be extended to certain solvable groups. Now, I wrote down the Baumschlag-Solitar groups as being the one case that we fully understand. There's another case which would be very interesting to understand, and that's three-dimensional solved geometry. Now, that is still wide open, understanding quasi-isometric rigidity of three-dimensional solved geometry. Nevertheless, enough of the structure from the H3 case goes over that it's very suggestive, and the exactly analogous structure in the Baumschlag-Solitar case is what we use to understand those groups. And moreover, it's easier to see that structure first in the case of solved geometry, so that's what I'd like to explain. Okay, so let's take M to be a 2 by 2 integer matrix. Trace, absolute value trace greater than 2, so this is a typical hyperbolic matrix, an Anosov matrix. And we construct a group G sub M, Z2, semi-direct Z, where the action is given by this matrix. Okay? Now, Z2, this is a lattice in R2, and the Z2 action on R2 extends to an action of this group, where you're stretching along the unstable eigendirection, contracting along the stable eigendirection. This is, of course, not discrete. And so to make this action discrete, you add one more dimension, and that's how you get solved geometry. So you do a little coordinate change. So you let x equal the unstable eigenvector coordinate, and y equal the stable eigenvector coordinate. Now, this is a case where I'm honestly not quite sure where the un goes, so you'll have to forgive me if I get this wrong. And then you have solved geometry, which is a geometry on free space. You can think of it as a solvable Lie group, and this is a left invariant metric on this solvable Lie group, and the metric is e to the minus 2t dx squared plus e to the 2t dy squared plus dt squared. And now the action of G sub m on R2, then this indiscrete action of G sub n on R2 then becomes discrete when you stretch it out in the vertical direction. So GMX on solved geometry. And now there's three interesting foliations here. First of all, there's the vertical flow, the flow in the t direction. Okay, and now in the x or y. In the, so you go up, t is large, this is tiny. In the x direction, you have the stable, the weak stable manifolds. Okay, so these are xt planes, and in fact each of these planes inherits a hyperbolic metric. So leaves are isometric to the hyperbolic plane. At this point, it's nice just to have a little picture. This picture doesn't look like much, but here's a typical flow line of G, and then here's, say, its weak stable manifold, its weak unstable manifold. You have other flow lines, and these distances are contracting exponentially. Other flow lines in the unstable guys, they're contracting exponentially when you go backwards. Okay. So W U is the weak unstable foliation. Okay. Now, so here's a conjecture. The conjecture is that a quasi-isometry of solve coarsely respects these foliations. Okay, and then a theorem would be that solve is quasi-isometrically rigid. This conjecture implies that theorem. Okay, so let me show you now the corresponding objects in the solvable Baumschlag-Solitar groups. So first of all, let me just give you the ordinary picture that a combinatorial group theorist would draw for the solvable Baumschlag-Solitar group, BS1N. Okay, let me draw the picture for n equals 2. So you would draw a little fundamental domain for the universal cover, which looks something like this, and then here's B, A, going down, B inverse equals A squared. And now you glue up the B's and the A's, that gives you a 2 complex with this fundamental group. And now in order to describe the universal cover of that 2 complex, you develop this picture out. Okay, so BS1N acts on a complex XN, which looks like this. Now, what you should think of when you look at this picture, it looks like the first thing you say is, well, there's a Euclidean rectangle. But unfortunately, these sides have, these little A sides down here appear to have half the length of these big A sides. So you should really imagine this picture in the hyperbolic plane. So here's the upper half space picture. Here's a horocycle, y equals 1. Here's another horocycle, y equals log 2. So you want to construct this object here in the hyperbolic plane. And now you see that these A edges do have the same length. So this is a little brick with 2 horocyclic sides, 2 geodesic sides, a little horobrick. And now you can start to tile hyperbolic space by these horobricks. So for instance, let's put them end to end, and you get a picture like this. Okay, and now if I were to go one level up in hyperbolic space, I would get a picture like this. Yeah, upper half plane model for hyperbolic space. All right, and so by continuing this scheme upward and downward, I'll get a tiling of the hyperbolic plane. And this tiling of the hyperbolic plane will live in the universal cover of the complex as I'm attempting to construct it. However, you can see that I've violated a basic rule in the construction of universal covers, because there's a I also have to glue on a Hora-brick like this, and like this, and like this. Okay? Well, because, you know, the picture has to be homogeneous. I have to see A edges glued to A edges in every possible way, at every possible A edge. And there's 3 A edges that are glued together. All right? So what you see in the universal cover of Xn then is this branching behavior, this upward branching behavior. Whenever you get to the top of a row of Hora-bricks, in this case n equals 2, it branches into 2 rows of Hora-bricks. Each of the top of those branches into 2. Each of the top of those branches into 2, and so on. So the universal cover has this nice topological structure of being constructed out of infinitely many, uncountably infinitely many copies of the hyperbolic plane, all branching together in this manner. And you can keep track of this branching by writing down a directed tree. This is the case of n equals 2 again. Every vertex has 1 edge coming in and 2 edges going out. And this tree has to be homogeneous, so it continues up infinitely. It also continues down infinitely.
What your construction looks like the natural extension for the map D squared in the unit disk.
If I understand what you're saying, I think I'll describe it in a minute.
You can say a two-sided orbit for the map Z squared.
Two-sided orbit for the map Z squared.
This tiling is a kind of tiliness which you can think of associated to the map Z squared, just split it to some plane.
Okay, I'm not sure I understand you, but okay. So the complex then, Xn universal cover, then actually has a projection to this tree. The group acts on this tree. And for those of you who know the language of combinatorial group theory, this is actually a Bass-Serre tree for the usual H and N decomposition of the Baumschlag-Solitar group that I'll write down in a minute. And then because of this branching behavior, whenever you have a line in this tree, if L is a bi-infinite directed line in this tree, then the inverse image is an isometrically embedded hyperbolic plane in the universal cover. Now, this tree has an uncountable space of ends. There's one special end down in the downward direction, and then there's uncountably many ends in the upward direction. And that collection of ends is in one-to-one correspondence with isometric embeddings of the hyperbolic plane in this complex. Okay. Now, what I would like to do now is to give you a slightly different take on this same picture and show you how this picture is very similar to this picture here in solved geometry. Now, this Baumschlag-Solitar group here is a semi-direct product of Z1 over n by z. The action of z on this z1 over n is just multiplication by n. And in fact, you can see a matrix representation n to the k x 0 1 where x is in z1 over n and k is an integer. So you have this nice matrix representation. All right. Now, z1 over n, you want to think now back to the examples I was looking at before of semidirect products of z2 by z. z2 is a lattice in R2. z1 over n is a lattice in R cross the metric ring of n-adic rationals. Okay, so when you have you can take z1 over n and embed it in R in the obvious manner. It's a dense embedding. You can embed it in the n-adic rationals in the obvious manner. It's a dense embedding. Take them together and you get a lattice embedding. Okay, and then the action of this lattice on R cross Qn extends to an affine action of BS1n on R cross Qn. And in fact, the action of the Baum's-Log-Solitar group on each of these factors is given by these matrices interpreted as fractional linear transformations. So fractional linear transformations acting on the reals and the n-adics. Okay? And now this action is indiscrete, but you can resolve the indiscreteness by adding on another direction. That's the vertical direction in this tree here. And you get a certain flow. Okay. So you get a flow, which I'll call Fn, and topologically this is just R cross Qn and then crossed with R, and it has a metric which I'll put quotes around. And the formula for this metric is just exactly the same as the formula for the metric on solved geometry, except, of course, that you can't do that, but I'll do it anyway. E to the minus 2t dx squared plus e to the 2t dy squared plus dt squared. Now, this unfortunately doesn't make sense because it's not a manifold. But then if you make sense out of this metric in whatever way is most natural, then you get a metric structure on this flow space, and you get a properly discontinuous co-compact action of BS1n on this flow space Fn. Now, how does it match with this picture over here? Well, the way to envision this flow space is to take this tree and take a very, very sharp knife, and wherever you see two guys coming in like this, just split all the way down to infinity. Split down to infinity. Split, 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 split. And you get this uncountable collection of lines here. And then for each one of those lines, you have a hyperbolic plane. So these hyperbolic planes Okay, so we've got these three foliations. I'll just write the flow space as one of the foliations. Then we have the weak stable foliation. And
Where are the foliations?
they are living in this flow space. Maybe I should call them laminations since it's not in a manifold. Let me call them, and since that's in my title. Okay. This space, what's the local topological structure of this space? Real, cross, Cantor-set, cross, real. Okay. So you have the weak stable foliation, and the leaves are copies of the hyperbolic plane, and the leaf space is the n-adic rationals. So this end space up here should be thought of as a copy of the n-adic rationals. So there's one of these hyperbolic plane leaves for every n-adic rational. And then you also have the weak, I should call these all laminations. Lamination, lamination. The weak unstable lamination. Now this is where it really gets uncomfortable because the leaves are copies of Qn cross R. You know, so one leaf is this picture here. Fortunately, the leaf space is much nicer. So the leaf space of the weak unstable foliation is the real line. Okay, now I spoke back earlier about this amazing coincidence in hyperbolic space, that the unstable leaf space and the stable leaf space in some sense are identified into the same object. And that doesn't happen in the solved geometry case. The unstable leaf space is one copy of R, which you identify with, you have the x and the y axes, and you identify the unstable leaf space with one of those axes and the stable leaf space with the other axis. And here, you similarly have these two different leaf spaces. Okay, so this Qn, I think of this as being one boundary. So this is the upper boundary of the complex, and R is the lower boundary of the complex. Okay. So now to justify this terminology, let me start to give you some sort of steps in the proof of our results about the Baumschlag-Solitar groups. So the first main result is, so remember the general setup. If you have a group quasi-isometric to your space, then it has this quasi-action. You want to know what geometric structures of this space are preserved by this quasi-action. And so a quasi-action of a group G on xn tilde coarsely preserves these three foliations, the lamination by flow lines, the weak stable lamination, and the weak unstable lamination. And in fact, even a little more is true. It actually coarsely preserves the strong, stable, and I have to be careful here. I want to say coarsely respects. What I mean is that it can permute leaves, but the image of each leaf is a bounded distance from some other leaf. Okay, so it coarsely respects these, and also the strong, let me say the strong, stable, and unstable foliations as well. Oh, yes. Well, okay, so since this is quasi-isometric to the flow space, then quasiaction on one is a quasiaction on the other as well. So it's probably, yeah, in this setting it's probably better to think of the quasiaction as being on the flow space. Okay. And the order in which you prove this is, well, the first thing you do is you prove that these hyperbolic planes are coarsely respected. And that uses very much the topology of the space XN universal cover, the fact that it's this two-dimensional complex, and so the two-dimensionality of it is used very strongly. And then that's combined with some coarse topology arguments due to Farb and Schwartz. And then once you have that it coarsely respects the hyperbolic plane leaves, okay, so first you prove that it coarsely respects the hyperbolic planes. Okay, so those are the leaves of H2. And then that it coarsely respects the strong, stable leaves. Those are just the horocycles in the upper half plane picture. And once you have that information, then you start saying, okay, suppose I have a quasi-isometry of upper half space which coarsely respects the horocycles. And now there's a sort of Folk theorem from conformal geometry that the induced boundary map on the lower boundary is simply a BiLipschitz map, and that there's an induced transformation on the horocyclic, the transverse parameter of the horocycles, which is simply a strict translation of the hyperbolic distance. So, and then that's enough to give you that it respects these other structures as well. And so the output of this is that G acts on these two boundaries, the upper boundary and the lower boundary. So now you have an action, and now you want to figure out the analytic quality of this action. And I already said briefly how that goes. It comes down to the fact that a quasi-isometry of the hyperbolic plane which coarsely respects the horizontal horocycles in the upper half space model has the form of a BiLipschitz homeomorphism of the real line. So here's the upper half space model, and here's the real line, crossed with a translation of the hyperbolic length parameter. Okay. And so what you get from that is a BiLipschitz homeomorphism of the lower boundary. And then you work more, and you also get a BiLipschitz homeomorphism of the upper boundary, the Qn. So that's step 2. Okay. So now remember where this group came from. This group G was, I'm now doing the proof of the quasi-isometric rigidity. So step 1 here is you assume that G is quasi-isometric to this space. So now you have these actions being BiLipschitz. Now, they are not uniformly BiLipschitz. In fact, if you look at those matrices I wrote down, and you interpret those matrices as acting on the real line by fractional linear transformations, those are affine homeomorphisms of the real line, and they can stretch more and more. In that case, however, they may not be uniformly BiLipschitz, but they are similarity maps. So this action here is a uniform quasi-similarity action. Okay. And so now the theorem you need is that a uniform quasi-similarity action on the real line is quasi-similarity conjugate to an affine action. So this implies that the action of G on the real line is conjugate to an affine action. This is very similar to a theorem that was proved by Hinkinen. He was attempting to generalize the results of Sullivan on the two-sphere and Tukia on higher dimensional spheres down to the real line. And his theorem says that a uniform quasi-symmetric group action on the real line is quasi-symmetrically conjugate to an affine action. And what we discovered is that you go through his proof almost line by line, and it translates into this statement here in this other setting. So the final act then is to show that there's a few things that you have to show. Okay, so you have to show that the kernel of this action is finite. So that's where the finite kernel comes from in the quasi-isometric rigidity theorem. You have to show that the stretch group G so this is the stretch homomorphism. You should have to show that the stretch group is infinite cyclic. Okay, and then at this point you have that your group G modulo a normal subgroup is, well, it's a solvable group. It's got a homomorphism onto an infinite cyclic group with an abelian kernel. And now you apply some tools of combinatorial group theory. Which imply that G modulo the kernel is abstractly commensurable to one of these groups, BS1n. Okay. Now, I didn't say anything about the classification of these groups among themselves. And it uses the same circle of ideas. What it comes down to is that if you have BS1M and BS1N quasi-isometric, then you discover that you get a BiLipschitz homeomorphism between their boundaries. And now Darrell Cooper analyzed that situation, and he proved that the M and the N are powers of a common integer. So where are we attempting to go from here? We have worked to some degree on this conjecture about solved geometry without resolving it. And so for the moment, we are trying to understand higher dimensional generalizations of these solvable Baumschlag-Solitar groups. So let me give you our theorem there. I'll give you the classification theorem because we don't have a quasi-isometric rigidity theorem. So suppose that M and N are n by n matrices of integers with absolute value of determinant greater than 2. And then you define groups GM to be Zn, semi-direct Z, Gn to be Zn, semi-direct Z, using these matrices. And then the theorem is that Gm is quasi-isometric to Gn if and only if there exists an integer k, positive integer, such that the powers of these matrices have the same Jordan form over the real, over the complex numbers, have the same Jordan form. And so you can go back and compare this to the classification theorem for the solvable Baumschlag-Solitar groups. That's the case of 1 by 1 matrices. And the machinery here is, once again, it's got a lot of dynamical systems in it, a lot of stable and unstable and center manifolds. It uses the shadowing lemma in order to prove that these various foliations are preserved. Okay, I'll stop.
Are there any questions? Actually, I have one. With the solved geometry, with your conjecture, what do you do for the replacing the Sullivan Tukia kind of theorem?
You can use this right here, because as soon as you've proved that the foliations are preserved, then you get an action on the lower and upper boundary. Lower and upper boundary are now copies of R, and those actions are uniform quasi-similarity actions. And so the tool's already there.